After that rousing start, my name is John Handler. I'm a solution architect, and I specialize in Amazon CloudSearch. Today, I'm really excited to talk to you about how to build search into your application using Amazon CloudSearch. And I'm going to really give you a soup to nuts sort of description of how to think about your problem, your search problem, how to get the data together, and how to support it, support the search that you need in your application. So we're going to start out by looking at an application that we're going to walk through how to build this in this session. So what we have here is an application called Build Your Playlist. And you can see that we have a very typical search interface. This includes a search box where users can enter text searches. It shows search results. And typically, again, in a typical fashion, we have facets that would allow users directly to drill down and to narrow their search. And we have sorting that brings the best results to the top. And ultimately, our users will add this to their playlist, and we'll hear all about that. So we are going to take this as our example, and we're going to start at the very beginning and build this all the way up. But before we go there, why should we care about search? Well, more and more these days, search is actually an interface that lets users get to the data, to your data, that lets users get to the functions of your applications. So on the web, search is used to, on a site like, say, Amazon.com, search is used to bring people to products that they want to buy. Desktop applications, including email programs, spreadsheets, all use search to help you to get to the piece of data that you actually care about or want to see inside that program. And mobile applications on phones, et cetera, increasingly search is becoming central even to locating the functionality that you're providing in your application and that people need to get to use your application correctly. So all of that means that the search experience itself really drives revenue, it drives user satisfaction, it drives retention, and search itself is a core piece of an application that you want to build. And today we're going to talk about Amazon CloudSearch. Amazon CloudSearch is a fully managed, full-featured search engine provided to you as a service in the cloud. It's a very simple interaction model, push data, pull query results, and we'll get into some depth about that. But a little overview on the product. It's extremely easy to get started, and it's easy to integrate into your application. It also provides automatic scaling and takes all of the operational burden of running a search engine off of your shoulders. So looking at these, CloudSearch is integrated with the AWS main console. To get started with search, you walk through a very quick wizard, just a few clicks, and you'll have a search engine which deployed for you in the cloud. Along with our console integration, we have a dashboard that shows you the status of what's going on. It's a little bit busy to read, but a lot of information about your search domain. And we even have a test interface that allows you to run searches within the console on your data. CloudSearch is easy to get integrated with. There's three main interaction points. When you start CloudSearch, when you create a search domain is an instance in the cloud with all of the software and services that you need that support running your search engine. So there are three, as I said, interaction points. The first is you have a search service. The search service, available through HTTP, of course, sends search results back to you. It's available either API or console, and there's some IP-based access control that lets you control who can actually send searches to your search domain. Along with the search service, we have the document service. Document service is where you push your data. Again, it's an HTTP endpoint. It's a RESTful interaction. Simply post your documents in a format, as we'll review, simple JSON or XML format. This also is available direct to API through the console, and also we provide command line tools to help out with this. And there's access control for document service as well. On top of all this, there's DNS and load balancing that ensures that your search endpoints stay stable. Ooh, that's a hard one. Stay stable through all of the changes that are going on operationally for your search domain. Alongside the search domain itself, we have a configuration service that is the point where you control how your fields are treated, how your data is indexed, access policies for your domain, et cetera, et cetera. This is available through AWS queries. This is the AWS API. You can go direct to API. Again, command line tools and console as well. So this is the whole picture of the interaction with CloudSearch. Now, CloudSearch is automatically scaling, as I mentioned, and one of our features is that we take the burden of running a search service off of your shoulders. If any of you have worked with search, you know that there's a challenge to figure out, how do I partition my data? How do I deploy my data to hosts? I have to manage those hosts, and as my traffic grows and shrinks, I have to add and remove hosts from my search grid. Amazon CloudSearch does all of the heavy lifting for this for you. So when you start your domain, you would have a single search instance with one partition's worth of data. As you send data to CloudSearch, you're actually going to increase and fill up the RAM of that instance. And at some point, when you overflow, CloudSearch would build a new index, deploy that new index with a second partition for you behind your stable DNS endpoint. So without any work on your part, other than pushing documents in, CloudSearch would scale out to fit the data that you're putting in. As you continue to send data, CloudSearch will continue to build and deploy indices in the amount of hosts that are necessary to host that RAM. Similarly, CloudSearch will scale for traffic. So we'd start out with a certain number of partitions with one host. As you're sending more traffic, CloudSearch is using CPU to serve those queries. When the CPU goes over a trigger, then CloudSearch would add additional copies or replicas of your partitions to serve the traffic. And similarly, as you send more traffic, CloudSearch would add additional replicas. And of course, CloudSearch will scale down as well as your traffic dies down. So we really have much of the benefit of the pay-as-you-go and pay-for-what-you-use AWS model. Okay, so that's a really sort of broad overview of CloudSearch. So let's get into some specifics and talk about how to build our application with CloudSearch. So, you know, music is something that people really relate to, and different music has different meaning for different times of your lives. When I got married, we actually created a CD. Everybody remember CDs? They were round, they had music on it. So we created a CD, and we handed it out to all of our friends and relatives. And that was our wedding CD. Now, we recently, actually Monday, got remarried at the Graceland Chapel. And as part of that, I thought, well, you know, it'd be nice if we went through that experience again, created a playlist, and, you know, handed it out, or a CD, and handed it out to our friends and family. Now, of course, we don't have CDs anymore. We have playlists, and we do social networking and sharing. But I thought, you know what? There's an application in there. People relate to music, and if I could actually go online, bing, 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 search for songs, create them as a playlist, share it out to my friends and relatives, that would make a nice application. So we're going to do that. And we're going to use a data set called the Million Song data set. This is a publicly available open source data set containing songs by title and artist, and as we'll see with other information. And we're going to put that into search so that people can search for songs that they want and then build playlists out of them. And that's our application. So I wanted to give you a feel for what's in. So when we're thinking about that, the first thing we know already is we're going to be searching for songs. And so it's going to be important to have a collection of songs. So the Million Song data set includes a set of songs with information like the title, the year, the artist name, And it has a number of measures, things like danceability, hotness, artist familiarity. There's actually about 100 different integers that you can pull out of there. This is just a quick sample. So we want to start with that and say, okay, we know we have title, we know we have artist name. Those are things we want to search. We want to be able to narrow by year, and we want to be able to bring all of that information. Okay, so here are the steps that we're going to sort of go through. We need to create a CloudSearch domain. We're going to identify our supporting data. We're going to talk about how to get that structured and uploaded. We're going to configure our domain to support the search that we want. We're going to improve our ranking so that the best results come to the top. And we're going to integrate it with a front end. And then we'll talk a little bit about how to keep it up to date as things change. So creating a CloudSearch domain. As I said, this is a very simple process, really involves just a few clicks, and a domain is up and running and ready for you to start pushing data in. We'll take a little bit more time talking about the use case and supporting data. So looking at our interface again, we see that our user has searched here for Rolling Stones. Somebody searches for Rolling Stones, we would expect to match mostly the artist Rolling Stones, but also if things were in the title, we'd like to bring that as well. And these are the results that come back initially for Rolling Stones. If we look at an individual search result, what we'll see is, again, we have the song title, the artist name, we're showing a familiarity and a year. So these are pieces of data that we want to hold on to, and we say, okay, those data are important. We want to make sure that we include those in what we send to CloudSearch. The search engine will use them. In addition, we were showing facets. In order to do faceting, we obviously need the data to do the faceting. In this case, we have the artist again, a genre, which allows people to narrow by pop, rock, all of that, and a year, which allows people to narrow down to particular years so that they can see search results for that year. So these are all of the pieces of data that we have to bring together into our single search document. That's what we're going to search over. So once we have our document, we need to, our sort of abstract document defined, we need to then take the data that we have and prepare it and upload it into CloudSearch so that those documents are in the search engine. So CloudSearch documents are formatted in something called SDF. This is Search Data Format. It's really a very lightweight JSON or XML wrapper around each of the documents in our system. And we'll see an example of that. One important point is that the source data itself is usually maintained in a system outside of the search engine. So in this case, we have million song data set is not maintained. The system of record for that is not our search engine. And that's a typical pattern. There will be some external system that owns the data, and then we'll have to build a process to pull the data out of that system and push it into the search engine. So once we've done that, we can emit that SDF and we can upload it. And looking at it sort of schematically, we have our million song data set, all of our songs. We're going to create SDF. Now, SDF itself is a batch format. So we'll be able to put together multiple search documents into a single batch for upload. And we'll post those to CloudSearch. So here we see an example of an Sdf batch. As you can see, it's a JSON array. If you can't read JSON, don't worry about it too much. Within the batch, we have single records separated by commas, and each record is a single search document. In this case, we have an add document. CloudSearch documents can be either adds or deletes. If you add a document that's already there, it will update that document to the newer version that you're sending. Along with the type, we have some identifying information, an ID, a version number, and a language. And then we have a collection of fields. Fields are name-value pairs, and these are the fields that you can search over, that you can retrieve, and that form the sort of backbone of your search application. And I left one out there because fields can be either single or multi-valued, and they work the same. Okay, so we now have our million song data set. We have it in batches. It's all prepared. It's in SDF. It's uploaded. Now we need to configure the domain so that we can tell the search engine, for instance, that we want a facet and that we should retrieve facet counts for, say, the genre. CloudSearch has three different base types. The first type is a text type. And text types are text processed. So they're split into tokens. Stemming is applied, stop words are applied, synonyms are applied. And they are really good for matching user terms. So when user types Rolling Stones, we want rolling, if they type rolling, we'd like rolling to match the title, rolling in the dew, or we'd like to match rolling to Rolling Stones. We use text fields for that. Along with the basic types, CloudSearch has three different field options. The first option is result enabled. Result enabled fields can be returned with your search results. General best practice is not to put a lot of result enabled fields in there. In fact, because there's a system of record, best practice is to put nothing but IDs for return. And as you get your results, go to your secondary system, pull all of the data for that result, and then use it to display the UI. But you can result enable fields, and those can be useful for a lot of reasons, like pointers to S3 objects or pointers to your database. The second type of field is the literal field. Literal fields are not text processed, so they are not tokenized. The term rolling would not match Rolling Stones if that was a literal field. It must be a full field match, exact match. The second option is Facet Enabled. And CloudSearch faceting is really very simple. You simply say, I would like to retrieve facet counts for this field. So, and the final option is Search Enabled. Especially for literal fields, you might want to search those separately. So this allows you to do structured search with Boolean expressions mixing different fields, provided that they're search enabled. And the final field type is integer. Integer fields are, not surprisingly, integers. And they are used for ranking, and they can also be used for faceting or narrowing. And I wanted to show you a screenshot of what this looks like in the CloudSearch console. What you're seeing here is the piece of the console that allows you to set the configuration for your domain. You can see it's very simple. We have the list of fields, a drop-down for the type, a few checkboxes for the different options, and it literally takes 2 minutes to configure your domain to do what you want it to do. OK, so we got our documents. We got them uploaded. We have our domain configured to support our faceting, to support our text searching. And now we're going to talk a little bit about ranking. So you can see here the results for Rolling Stones. CloudSearch uses a default text relevance function, which is comprised of a TF-IDF and a proximity measure. So when you match text to text, we're looking for both how many terms matched and how unique were those terms for the match, and then how close together they were. So the scoring for each document takes those into account, and it brings the highest scores to the top. In this case, we have Heart of Stones for the Rolling Stones. That's good. We're glad with that one. And then we have Under the Boardwalk by Rhythms del Mundo featuring the Rolling Stones. Not as good a match, but text relevance-wise, that's the one that comes up. And then we have one which I believe is in Portuguese, which I can't read, but also just the pure text relevance itself brings that one to the top. And then we continue on with Rolling Stones. So really what we'd like to see for this query is we'd like to see songs by the Rolling Stones. Now, fortunately, we have an integer measure that can help us out with that, and that's the artist familiarity. So what we can do is define a CloudSearch rank expression, which allows us to mix algebraically values that are in our document with our text relevance function or with other values in our document to provide a scoring criterion for each document. In this case, we give it a name, and we mix the text relevance with the half of the artist's familiarity. There's a little bit of number tweaking that you can do to make sure things line up correctly. But the larger point is we can define a function for each document that lets us score that document and hopefully bring the correct results up to the top. Once we reorder by that ranking function, what we can see is we have a number of matches by the Rolling Stones. Those have moved up to the top because the Rolling Stones are a more familiar artist. CloudSearch has a lot of flexibility in rank expressions. You can define custom rank expressions to do just about what you want. Okay, so we have our search, we have ranked, we're ranked nicely. Now we want to talk about the interaction with the front end, and how does that look? I wrote a really simple PHP script. You can do this any number of ways. In PHP, file get contents is a call that you use to retrieve a full result from an HTTP endpoint. It's just like a curl call. We include our CloudSearch endpoint here. Again, this is unique for our domain. This is our search endpoint. And we include in the URL path, we point to the search resource. And then we include our keywords in the query. And Q equals is a search parameter that tells us to search against all text fields. We can tell CloudSearch to return different fields. In this case, we're returning the title, the artist name, and the year. We can also facet, so we tell CloudSearch facet by artist name, year, and genre. And we can also specify a ranking function, how to rank the results. You could type all of this into a URL. This is simply an HTTP endpoint. It's a simple HTTP GET. What comes back, we can just JSON decode it, inflate it into objects, and use those objects to populate our UI. So looking a little bit in detail at some of the search results, for a simple search like Rolling Stones, we'll get some information from CloudSearch that tells us what the query was, what it was ranked by, and how many hits there are. Each hit is a single document that CloudSearch has identified as matching this query. In this case, Rolling Stones finds 204 hits. Oh, that wrapped poorly, but for each hit in a simple query, we'll receive the document ID for that hit. And again, the best practice is to get a result like this and then take those document IDs, go to your secondary system, and inflate them. Happy to answer questions after. So let's look at search results with some return values. Again, for each hit, if we specify that we want return values, what we get out is the ID and then a data section that provides us with the values that we sent into CloudSearch when we created this, when we posted this document. In this case, we have artist familiarity, name, text relevance. I'm returning text relevance here because that lets us sort of look at it and see how they rank against one another. That helps us do tuning for ranking. Title and year. And we can look at also what the result looks like when we do some faceting. So after the section of hits in our search result, we get a section of facets. For each facet, in this case genre, we'd get a list of the possible values along with the counts for those values. And if you look at that, you can see it maps almost one-to-one with what you see typically in the left rail of an application. You would see pop is 126 and rock is 125, alternative 109, etc. So that's kind of a walkthrough. We started out with identifying our application. We thought a little bit about the data that we would need to support the kind of searches that we wanted. We talked about how to get that data, structure it, and put it into CloudSearch, how to configure our domain. Talked about the integration, how does the communication look back and forth. And ultimately, we'd like to see our users come and build their playlist and have their list of songs, hopefully buy those songs from us, and be excellent. Okay, so we also want to talk about keeping ourselves up to date. As the system is in motion, and typically your data is not static, and as you have updates to your data, You want to capture those updates. So for instance, in a social networking scenario, if you have users thumbing up different items, you want to be able to push those scores into your search engine. So what you do is you capture the updates as they occur. Then you would create SDF documents for each of the changed documents in the system, assign them a version number. Again, CloudSearch serves the highest version number for any document that you've pushed in. So for a particular document, you would pick a higher version number than that you sent before. And best practice there is to use a version number, a Unix timestamp. Unix epoch is a good one, as you're sending it out. That means that will be monotonically increasing, and your updates will always apply. You want to batch your updates together and upload them using, again, a similar process to what we did in creating the initial data set. Your updates are applied to the index, and they're available in near real time. There's no additional work on your part. You don't have to build indexes. You don't have to worry about partitioning. Simply post your updates, and they come in near real time. OK, so I am going to turn it over now to Matt Norton from PBS. He's the Director of Application Development, and he's going to talk a little bit about CloudSearch from a user perspective.
Thank you so much. Hi, I'm Matt Norton, as he said. I'm from PBS, and I'm essentially a tech lead there, and focus mostly on our mobile applications, but I've had some involvement with our CloudSearch efforts. So, essentially, the two main use cases that we had were, first of all, we were working on our mobile video portal, which is a responsive website trying to take advantage of all the new platforms out there. And the search that we had, well, I can get into the details of that, but essentially, we had the new video portal we wanted to get search on, and then we also wanted to get a solution that we could add search to all of our applications at PBS. So we have a lot of one-off applications, and we wanted to find an easily plugged-in search solution for all of our apps. So our video portal, we needed a mobile-specific search. And we had RAMP, and we still have RAMP on our main website. And that was working OK, but it was going to cost us a lot of money, and it was going to be quite a bit of effort to make it be able to give back mobile-specific results. So we're looking for something that we could do quick, lightweight, but our team was very busy working with responsive web and trying to figure out mobile video. And so our vice president, John Brentzel, who some of you guys may have seen in some of the other Amazon talks from PBS, he's a very hands-on manager, and he was the guy who got us into AWS there. But he's not a developer. And the reason I bring this up is that while I'm very glad John brought up kind of how you do exactly what we did and how to get your app search, it actually is simple enough that our vice president, who is very sharp, was able to come in with very basic Python and get a prototype up and running. And so he did that. He started off taking a CSV file of all of our video metadata, and he uploaded it into the console directly, I think. So there was no programming involved at all. And then he started doing queries, started to play around to see if this was a solution that was good enough for our data. And he liked it, so he started playing with Python and Boto. Boto is the Amazon SDK for Python. And it has a CloudSearch module as well. But essentially, we started taking our data from our API and going through Python, shoving it, and as it was updated, putting it on a schedule into up into CloudSearch. So he also developed a quick client app with a little help to play with the search engine. And basically, it let us look at all the queries, the facets, and you can see it's not very clear there, but essentially you can search, and then it gives sort of what you would need to query directly the API if you were going to put it into your app. But it also lets you visually play around with it. So this is what ended up happening. It ended up becoming a production product with the vice president's work. So we had a little client-side work, obviously, to link it up, but it was just drop in a query into the app, or in this case, it's mobile web, and we started getting results back. And that's live, that's our mobile website. We only have about 60,000 video assets in there right now, which is sort of our live mobile catalog that we've transcoded. But it's, and we do update the index, like I said, on a regular schedule. So with the Python stuff, those are just a little details of how we implemented it. And it works very well so far. It's very fast. It's 26 milliseconds average response time. And our developers are very happy. As a matter of fact, with all of the facets, everything else on there for the querying, our developers have asked, hey, can we switch over to just using CloudSearch to get the data? So, and by that I mean even for browsing. Basically, I don't know if it's misusing CloudSearch, but it's basically using it in a very fast, flat kind of search. So we'll do a quick search on, like he was saying, Rolling Stone. So we'll look for masterpiece videos, and it will give us all the masterpiece videos. And so it's essentially a search, but it's very much, we're not searching on text. We're at that point looking at a literal and kind of drilling down through it. So that has, our API, we haven't had time to go back and make that faster, and with 26 milliseconds and scalable, everything kind of just is managed for us. It's been excellent. We've used some of the options that CloudSearch currently has, like ranking. We've given title a little more precedence over description. The publishing date, kind of how recent the video is, we've factored that in. We've started looking at other things we can do for that as well, trying to get the search a little bit cleaner. But it is very good, like I said already. We've used synonyms. A lot of people come in mistyping stuff, particularly on mobile. So we look through our search results and we see what the top terms are that have no hits, and we start entering those in on the side, just like we do in RAMP actually. And so we also have a couple stop words, which are just common terms that people search for that are also in all of our videos. Yeah, so the UX is actually taking advantage of the facets now. And now the next step is trying to pry it away from the VP. So we're trying to make this into a serious product with, staging environments, QA environments, and in order to kind of put more ops and product around it, we need to eventually get it into a product team. So that's kind of one of our next steps. And then the second use case we have, excuse me, do you mind if I grab some of this water? How many is this? Sorry. The second use case we had was adding search to our other apps and admin tools. And so just very briefly, we developed a CloudSearch backend for Django Haystack, which is, you can go look at it, but it's essentially a module that you can drop into your Python Django apps, and it syncs all of your models and all your data from the ORM. It automatically pushes it up in the CloudSearch and will really whatever search backend you choose. They didn't have a CloudSearch backend, so we wrote this and open sourced it. It's not quite ready for production, but we're working on it, and there's a couple things I think we need to either look at Boto, getting some of our changes pulled into there before we can really consider it production ready, or into the Haystack itself. And that's going to enable us for all of our small one-off apps to basically say, hey, I want to be able to add search to this very basic app, maybe just an app that our producers use or something, and it'll just be very trivial to say, yep, drop in the Haystack module and all of the data is searchable. So, and that's it. Check out PBS, donate to your station. No, I can't. Thanks, John.
Thanks, Matt. Thanks, Matt. I really love that story. The VP just went ahead and did it. So just to summarize a little bit, we talked about, like, as Matt was also pointing out, search really is a central part of your application, and it drives your user's ability to locate the data, the functionality, the pieces of your application that you want to provide to them. And it has been a difficult challenge to provide search in your application. With Amazon CloudSearch, you get a fully managed service that allows you simply to push in data and pull out search results in a full-featured search engine, which is fast and provides features like Boolean queries, faceting, ranking, customizable ranking, right out of the box. It's got the benefits of the cloud, so it's pay-as-you-go, no upfront costs, pay for what you use. And it lets you get up and running fast without focusing a lot of IT effort on operating your search service. It lets you innovate. So right now, we are running a free trial for new users of CloudSearch. You can use CloudSearch for 30 days free. Encourage everybody here to check it out. Spin up a search domain. You'll see in the console we have data sets that allow you to just try it out. And get up and running now. And thank you very much.